hoping to be here, but he's still stuck in a.
Yeah, he sent me an email.
We're trying to do a real theory seminar for the first time in like
I
10 years.
don't think he went to New
Yeah.
York. I think he's just.
because usually it's
Zooming in.
Yeah,
Wait,
but the-
Oh, by the way, congratulations. Yeah.
There's not a.
well, there's a theory lunch, but it was like a mix between internal, like, because the students have to give talks. So it'd be a weird mix between like
How much was it in Boston?
younger students
Much
and then like
Oh,
senior people.
Yeah.
And they've decided to split
Yes.
the actual theory seminar where there were extra people.
Food. We also had a food.
Danny Sleater, who's like the only
Probably.
person.
I don't know how much
Enough to remember,
it
like,
was, but
there used to be a seminar, I was like, yes, for 15 years I've been wanting
precise
to ask
measurements or
whatever.
whatever.
We're like, okay.
Ours is sort
Yeah,
of weird.
but,
Like,
like,
UCSD,
Our house is like.
people weren't
Right.
required to get
Yes.
seminars. It was more like if whoever was
Okay.
organizing
Usually they
how
also
lazy they
follow-
were,
Yeah.
there would be more.
Follow the
internal
driveway, but then
seminars.
the entrance is.
So if it was Russell, then it would be
Usually
mostly
also,
internal.
like- And they
There's a
didn't.
new assistant who's like Daniel Greer or
Yeah.
something, and we'd have people.
At some point I realized
Yeah, we
they shouldn't wait
one of the
anymore.
graduation requirements for PhD
Yeah.
students is like giving.
Brian had a lot of-
seminars.
Yeah, that's much
Yeah, so
work.
they-
You have to pass some
Oh,
committee and so on. At least once, but then many people end up doing it like many times.
Oh, interesting.
Does the committee actually?
Yeah,
Yeah.
staying at the NASA wing.
Historically, yes, I think.
I was often awake in the middle of the night by
He was
like
like
an hour.
You went to NASA wing?
Yeah, I went to,
Oh,
yeah.
You should become
Yeah,
a science
yeah.
people before you pass,
The GSA.
but I feel like the standard has.
So like I was
We had a
being
lunch
awake in the
seminar,
middle of the night.
it's like the student
That's what
seminar.
we're-
Because of plows.
Yeah.
But it purely
Because of
existed
power
because I was
trend,
mad that we
Palmer
didn't get free
Square.
food at the normal seminar, so I founded the lunch seminar, so we
I
could
think-
get
I
free
see.
food.
Oh, nice.
Yeah, I think it's
Yeah.
mostly.
I had Daniel Gaines funding, I was a funding student, so we had a ton of extra funding that I was using it with no restrictions. I spent hundreds and hundreds of dollars.
Just on Coke Zero.
Just on Coke Zero. Yeah, not much food, just Coke Zero.
That's it. Yeah, we gotta expand the tower.
we can
Yeah,
start.
tower in his office.
And one Diet Coke for Russell.
Okay, I think 10:30, so very, very happy to have Brian tell us about all the exciting win-win analysis. And then we will have Monday's talk on Thursday around 10:30. We don't know exactly, stay tuned. Okay.
Thanks. Yeah, so this is about the orthogonal vectors conjecture and non-uniform circuit lower bounds, AKA Sierpinski triangles, shallow neural nets, and Boolean satisfiability in that order. Okay.
Was that in the box title or is that is extra?
No, this is extra. This was definitely not, I don't think they would have allowed so many characters in the box. Yeah, yeah. Yeah, that's my favorite fractal, yes. It's also a very nice matrix. So this talk is about three things and how they connect together. But I guess like one of the bottom lines of this talk is that at least one of the following is true. This win-win type thing that you're even talking about. So either there is a very simple function that requires exponential size depth to neural nets. I will define very carefully what that is later. The very simple function is just the disjointness function or a simple 2CNF formula. And the thing is, it's a wide open problem to even show that there are functions in, say, exponential time with an NP oracle that require exponential size depth to neural net. So getting a very, very simple function that exhibits such a lower bound is a huge open problem. So either this very nice lower bound happens, or we get an incredible SAT algorithm. In particular, there's no known quantum advantage for SAT solving anymore. There's a deterministic algorithm for CNF SAT that runs in square root of exhaustive search time. So not only is this a major refutation of this so-called strong exponential time hypothesis, but it also implies circuit lower bounds of a different form, though. It's not. It's a completely different form of circuit lower bounds. So you can also think about it if you only care about circuit complexity for some reason, either circuit lower bounds or circuit lower bounds of different flavors. Okay. So one of the goals of this talk is to prove to you this theorem in full detail. So let's go through the three things that this talk is about. Thing one is an inductive sequence of matrices. So we have an M0. And for n at least one, we define M sub n, which is 3 copies of n minus 1 with an all zeros in the corner there. It's 2 to the n by 2 to the n matrix. And they start looking like this. And so you get a sideways Sierpinski triangle. It's a very nice little matrix. Right. So another way to define them, which is the way that you will have seen in TCS a bit more, is indexing the 2 to the n rows and columns by n-bit vectors in, say, Lex order. So in other words, starting with a leading 0, and then here we start with a leading 1. This is the so-called disjointness matrix. Because given 2 vectors, bit vectors, if I look at the youth row and vth column, it is 1 or 0 based on whether this Boolean formula is true. Okay, so we think of these vectors as sets, say SU and SV in the natural way. We have a 1 entry if and only if the 2 sets are disjoint. Okay. So this is a disjointness function, right? So this is well studied in communication complexity. Usually we think of Alice as holding a row and Bob holding a column, and they want to know whether the bit is 1 or 0. So it's known that disjointness requires n bits of communication between Alice and Bob, even if they have a non-deterministic protocol. If they have a co-non-deterministic protocol, it is easy. It's a big and. Okay. But yeah, it is in fact complete for co-MP communication in a certain sense. You can define in a natural way what is a co-non-deterministic protocol, where there's like sort of guess bits and you accept, or Alice and Bob conclude 1 if all of the possible runs of the protocol lead to a 1. And there's a sense in which disjointness is the hardest such function for such protocols. You can reduce any such protocol to like just calling disjointness. It's also known that disjointness needs essentially linear randomized communication. Okay, so even with randomness, it doesn't sort of help. They basically need to communicate their vectors. But in the quantum setting, we can actually get something like a square root in savings. Similarly to how you can get, you can compute OR in square root, and you can compute this AND of ORs of knots in square root n communication. And there are other like sort of probabilistic MP, Merlin-Arthur communication protocols, where you can also get square root n savings. So in other words, like Alice and Bob, besides Alice and Bob, there is a third party Merlin that looking at the inputs can communicate a square root n bit message, so that Alice and Bob just need randomness to conclude whether it's disjoint or not. And when they're not disjoint, there's a small probability of error. Okay? And these sort of protocols will actually be important for us, like in terms of like what we're trying to understand about how efficiently the disjointness matrix can be represented in various ways. So each of these facts can be viewed as theorems on representations of the disjointness matrix. So for each of these sorts of things, let's say in the Merlin-Arthur setting, this corresponds to some sort of matrix representation where I guess one of some number of matrix ensembles or something that corresponds to Merlin's message, but there's not too many such ensembles, and then I randomly draw something from one of the ensembles that corresponds to Arthur's thing, and then I have some condition that on all of the possible rows and columns, whatever I'm looking at, and like there is some choice of ensemble, like if the disjointness is 1 in that row and column, there is some choice of ensemble so that when I randomly sample, I'll always get a 1 entry. And then if they're not disjoint, then for all the possible ensembles, when I randomly select, there is some there's some chance that I'll have a 1, but usually I'll have a 0. So you can think of these communication protocols as being some ways of representing the disjointness matrix. Maybe for non-deterministic communication, it's a little bit easier to see. This is sort of like if disjointness required not too many bits of communication, this would correspond to some representation where I take the OR of some Boolean matrices, and there's not too many of them. It's so it's if I could do it with q bits of communication, there'd be 2 to the q matrices that if I OR them together, I will get the disjointness matrix. But this is saying no, in fact, you need about 2 to the n matrices to OR together to get this disjointness. So each of these is some representation of the disjointness matrix in some form or another. Each of these have their own kind of representation. I think with quantum, you can think of it as some sort of approximate linear combination of matrices, things like that.
Where the basic matrices are much simpler, or
So you can think of that as, I think, maybe some approximate side rank notion, for example, works for quantum. And these can just be basic -1, 1, 0 type matrices. They don't have to be very complicated. So it's a linear combination of these kinds of things. Yeah.
no, the question is, this is also a matrix, so what's the difference?
I just mean that each of these theorems, instead of thinking of it as a communication lower bound or whatever, you can think of it as some lower bound on the number of simple matrices you need, whose in combination gives you this matrix. Yeah, that's all I'm saying. Yeah. And because I'm just emphasizing this because that's the way we're going to look at this. We're not going to look at something in terms of communication, although you could. And there are some limits on what we are doing that other people proved in terms of communication, but they don't rule out our approach. So anyway, I just wanted you to think about it as, okay, I want to have some notion of simple matrix and have some notion of combining them, maybe a linear combination, maybe an OR of them or something. I want to know how many simple matrices I need to get this fractal. Okay. So one more formulation, which is useful for us. So given an n by n matrix, its nth Kronecker power is the n to the nth by n to the nth matrix, where I index the rows by m tuples, from 1 to n. So this, it's kind of blow up the matrix. And this entry is just the product of component wise of these entries. Maybe I'll write this thing down because this is important. So we have A, and then make sure I write it the same way. This is an important sort of way to get a bigger matrix from a smaller one. Okay. So very simple theorem, just sort of capturing what's going on in the recursion, is that m sub m is the nth Kronecker power of this matrix. We always write that too, so that's just useful. All right, and so suppose I have a copy of m sub k. I can always get m sub kn by taking its nth Kronecker power. That's a very nice little property. Follows directly from the recursive definition. Right? Okay. So that's thing one. Okay. So thing two is so-called, what I call shallow neural nets. Another way of talking about them as depth two neural nets with a sign activation. A more maybe standard circuit complexity way of talking about them is that they are sums of thresholds, sums of linear thresholds. If you look something like this, I've got n inputs, which feed into some linear threshold functions. So there's some weights, some real weights multiplied by these things. They're summed up, and we check whether or not they're at least a threshold. If so, they fire 1. If not, they fire 0. And at the top, there's just a linear combination being applied.
So is it a linear combination of these ones and zeros, or is it of the x1 through xn?
Yeah.
A linear combination of, oh yeah, this is a linear combination of the outputs here.
Okay.
Yeah. We could put, you can imagine there are Y's there. Yes. Yeah, so we could feed this thing reals. So people often study the case where this is computing some function from n reals to a real. And there are known results about that. So a theorem of Minsky and Papert is that every Boolean function whatsoever is computable by such a thing. And this is not too hard to show, but the circuit could have an exponential number of gates and wires. A gate meaning a circle and a wire meaning one of these lines.
Why is it called neural nets?
What's that?
Why is it called neural nets?
Because these are literally neural nets with a sign activation function. Like there's an entire community way bigger than ours, which calls them that. I mean, but yeah, and they're depth 2 because there's only like one activation layer. There's this one hidden layer.
It's like the x's are like the signals from the other axons,
Yeah,
and then you get them, and if they pass the threshold, you shoot.
they were derived to, they were at first studied by like Rosenblatt, like trying to model a neuron. So there's, I don't know, like, anyway. So a big question is, which Boolean functions, so we can think of as decision problems, so they from arbitrary bit strings to bits, represented as an infinite sequence of these f sub n's, which of them have a depth to circuit family with a polynomial number of gates? And now I'm talking about Boolean functions. I should be more precise about what does it mean for such a thing to compute it. There's multiple possible interpretations. One, you could require that this linear combination, when I feed it 0 ones, this linear combination is always evaluating to either 0 or 1, assuming that these are 0 ones. Okay, that's one kind of extreme choice of like what does it mean to compute. But the question is still open, even in that setting. A less extreme version is where you just say, okay, this sum is either 0 or non-zero. And I want it to be that when the function is going to output 1 on this input, this sum is non-zero. When the function outputs 0 on this input, the sum is exactly 0. There's a non-zero zero representation. And yes.
Is the NAT, like, what about if you just put another threshold on the top one?
Yeah.
That's different, right?
That's a threshold of threshold. This is something like, even more complicated, right? Because you could always have a threshold that models like these two representations too. Yeah, if you put a threshold, that's an even more. That's like, yeah, that's what is normally called depth 2 thresholds, which is also wide open in terms of lower bounds. Like there's only like a few such things now.
The weights here are non-negative, or they can be out.
It could be anything. Well, reals. Yeah, but what you can show is that if I restrict to Boolean inputs, then without loss of generality, I can think of these things as rationals where the numerator and denominator are at most like, let's say, n to the order n. So like by sort of studying like a linear program that defines what is happening here, you can restrict the weights if you're assuming that only Boolean inputs are coming here, and you want like thresholds that behave the same way as like your arbitrary one does. So yeah, so it's not like you can encode infinite things in this thing. Yeah, so I'm going to focus on this sort of non-zero zero thing, but yeah, even having like a linear combination which like always evaluates to exactly 0 or 1 on all Boolean functions, this question is still largely open, which is yeah, it's very surprising. Like it seems like this is not. I mean, that should be very extreme. Like, you know, only certain sums should have this kind of property, like, and they should be like exponential-ish or whatever. Like things based on inclusion and exclusion or something might be like that, but not just like polynomial size sums. So yeah, this is largely open, and the best known results for like say low complexity functions are. So Daniel Kane and I showed a while back that there are functions in P, such that these things, in fact, with a threshold at the top as well, need at least in the 1.5 gates and at least in the 2.5 laps. Well, divided by polylogs, that's what this tilde is for. Okay, so they need approximately this much, which is yeah, not a big lower bound. And if you like restrict to the special case where this sum has to be 0 or 1, like on all Boolean inputs, and exactly compute the function, then you can show there's a function in NP which requires n to the k gates for every single constant k. But this function in NP might need non-deterministic time n to the k to the k to the k or something like that, right? So for each fixed constant k, I can find some function in NP taking much more than n to the k time, which requires at least n to the k gates. So this is, I mean, it's an interesting lower bound, but it's still fairly weak. So this is sort of like all
Aren't all Boolean functions in NP, or am I
No.
confused? Like I thought SAT was in.
SETH is indeed an NP, but there's like a random Boolean function. Like, so here well, first we have to talk about decision problems.
Okay.
Right, so to talk about whether it's an NP or not.
I think I just misunderstood.
Yeah, like most of them are like that are just uncomputable. They're like not even RE or whatever. Yeah.
So the weights are confusing me, like
Yes.
at least in the probabilistic method, you can show you need an exponential number of gates of wires, right? Like
For a random function.
for a random function.
For a random function, yes.
Yes.
For a function, an function NP is not random.
Of course. No, I know.
Yeah.
It's I'm
Okay, sorry. But yeah, so yeah, you can show, I mean, yeah, in fact, like it's known that there are special particular linear threshold functions for which you need, n to the omega n like weights, like size weights, to compute them like correctly on all Boolean inputs. So yeah, is there something else I can help to allay the confusion? But yeah, the thing is that they can be quite powerful. We know that like one of them is not that powerful, like they can't compute things like parity, but like yeah, already like just 2 layers of them. It's difficult to even find like good simple candidates of functions that we think okay, definitely not. Okay.
I mean, parity, is that a candidate for this?
No, for this, no, because I can so pair like any symmetric Boolean function I could represent with like just an order n size thing. So like I can represent whether linear combination is exactly equal to something using like 2 of these things. One of them canceling out the other one if it's like too high or whatever. And then I can just pick the Hamming weights that I want and just take the sum of those. And exactly one of those most one of those will be true. So I can just take the sum and it will actually be a 0-1 linear combination. So even in the extreme case, like any Boolean symmetric function works. Yeah.
What is the function in P as the lower bound?
It is Andreev's function composed with an error correcting code. So there's this Andreev's function, which is like an addressing function, which has like where you take, so you have like an n-bit string and a log n bit string. That's the indexing function. So given like some I and the log n bits, you want to just report what the ith bit in the n-bit string is. And so Andreev's function is like taking XORs. So you put XORs on each of these log n inputs here. Okay, so you take like XORs of like n over log n things. So now you have like 2n bits in total. So you have like XOR of n over log n like coming into each of these log n things. And then this thing is like basically you put a particular error correcting code. So you take your input and you apply error correcting code to it, and that goes into your n-bit string. So anyway, it's like, yeah. So like Andreas function was used for like this random restriction method to show like in cubed formula lower bounds, but like when you apply this error correcting code, it lets you get away with a little bit more. Yeah. Okay. So I mean, I guess I should say that if the weights are small, like, either in the top or in the bottom, then there are like exponential type lower bounds known. So it's really like the weights on both layers that make the problem hard, like for us at the current time.
Do you have the lower bounds against random functions in this? It's
Yeah.
exponential lower bounds.
Yeah, for sure. Yes. Yeah. Absolutely. Yeah, because there's only so many functions that each one of these will compute, in fact. Like they can, anyway. Okay, so the third thing, which you're probably more familiar with, is Boolean satisfiability. But, I'll go ahead and put the definition here again. Anyway, we have a formula over m clauses. They have n variables. Each clause has at most k literals in it. Each literal is either a variable or its negation. Okay, and we want to output, say, a Boolean assignment that satisfies all the clauses, makes all the clauses true, or no if there's no such assignment. Brute force will take to the n. Is there a faster way? Well, we know this is a canonical NP-complete problem. So assuming P from NP, we're not going to get this, but there are these stronger versions of P different from NP that have become popular, and there's a ton of literature on them now. The first one is the exponential time hypothesis that for every k at least 3, k-sat can't be solved into the delta n time for some delta. So there's some perhaps very small delta for which you can't solve k-sat. Another way I like to say this is the k-sat can't be solved in 1.00001 time for some number of zeros. So there might be improvements on solving 3-sat over time. Like the best one is like 1.308 to the n, but the hypothesis is that these improvements will have diminishing returns and eventually stop at some constant, but we don't know what. Another popular hardness hypothesis, vastly strengthening P from NP, is the strong exponential time hypothesis. And this says that essentially for the CNF set problem, the best algorithm is about to the n time. So for every epsilon, let's say I wanted to improve in the exponent, to the n, I want to improve by some epsilon. Well, there's some k, some clause with k, so that k-sat can't be solved into the 1 minus epsilon n time. Okay. So another way of saying this is like, okay, suppose I just look at CNF set where I don't put this clause restriction, like this restriction on the length of the clauses. I just say it can't be solved in 1.99999 in time for every number of 9s. Okay, so you're not going to shave off the base of the exponent even by any tiny amount. And any amount that you do, it would depend on somehow on the clause with k.
How large should I think about M? I noticed you put the poly M there.
Yeah, for the purposes of these two conjectures, you can actually think of M as just order n. There is a theorem called the sparsification lemma, which says that actually, from the point of view of sub-exponential running times, it suffices to just look at the case of the number of linear number of clauses. So sort of without loss of generality for these two conjectures, think of M as order n. And this big O is like a function of the K that you started with, and a function of like the epsilon, like let's say I wanted to the epsilon in running time. Yeah, so that's actually important for us. So thanks for pointing out. Yeah, I just put the poly M so that people will, because some people will ask what happened to the number of clauses, and I just put that there because I usually don't have time to take an aside and tell you about the sparsification lemma, but here I do. So there we go. Yeah. I can tell you even more about sparsification if you like. But yeah, see, yeah, these are like.
And
yes.
so the CNF stat condition, is that equivalent to SETH? Like you can break it into constant?
Yeah, if you start with a linear number of clauses, then yes.
Okay.
Yeah, if you start with CNF set with a linear number of clauses, there's a way to get K set for some K, which depends on this leading constant.
I see.
Yeah. This is a nice result proved by Calabro, Russell Pagliazzo, and Mohan Paturi. So these are just some hypotheses that people make. So, like they're quite useful, like from the point of view of there's been a lot of work on these set algorithms, and none of them seem to get close to doing either of these two things. And so if you have people started a while back to say, okay, well, suppose I make this hypothesis. This is like basically saying that brute force is essentially optimal. Can I use it to show that other problems, are optimal? Like assuming this is true. It turns out that yes, you can basically get an entire, like a huge array of problems, like one of which orthogonal vectors we'll look at, for which like the obvious algorithm is optimal if if CNF stat requires brute force basically. So it sort of led to an entirely new kind of reduction theory, way beyond like NP completeness in a certain sense. And I'll make more precise what that sense is later. But yeah, there's a exponential time hypothesis also equivalent to, you can stick in a lot of other NP complete problems in here too, like vertex cover and Hamiltonian path and stuff like that. But not all NP complete problems are equal from the point of view of exponential time algorithm. So that's something, but there are like certain equivalence classes for which so SAT is not that special in this sense. Okay. All right. So let's see how to combine thing one and thing two. Okay. Right. So we have thing two, this sum of thresholds, and thing one, this disjointness matrix. So the question is, does the disjointness function, say when I fix an n, I look at the disjointness matrix, is there a depth 2 neural net family with a sub-exponential number of wires? Okay, so I think of disjointness here as just being, just being like, so let's write up here, disjointness on like x and y as this like as an and over all these clauses of not xi or not yi. All right, so very simple function. Does it have a depth 2 family, though, one of these sums of thresholds, where when the disjointness function is 1, the sum of the output is non-zero. When the disjointness is 0, it outputs 0. Does it have something with sub-exponential number of wires or gates? Okay, so can I get away with something other than just like there is a representation that takes to the n. Can I get something much smaller? Now, of course, if the answer is no, we have a breakthrough lower bound because we have very few lower bounds for sums of thresholds, and this is a very simple function. But if yes, then what happens? Okay, so what happens if we actually did manage to have a family? And now this is a non-uniform circuit family in the sense that for each value of n, there could be some sum of thresholds drop down from heaven, which happen to work, but it could be a completely different one for each value of n, right? So it can be hard to see like how this could be useful for us. But that's where thing number 3 comes in. Okay. So a surprise is that actually, if this disjointless function has a depth to a family with selection too many wires, then SETH is false. And this should not make sense at first because this kind of object is something that is a non-uniform circuit. I have a separate circuit for each input length. Okay. SETH is talking about something completely different. SETH is talking about having a single Turing machine type algorithm that, given any CNF formula, tells you whether or not it's satisfied or not. So they're literally about completely different models. Yet what we can show is that actually, even if you have this sort of non-uniform family, you can like take small finite pieces of the non-uniform family and then use that to get a set algorithm. This is sort of like the super high level idea of why this implication could even possibly be true. But another way to say is that let's say I guess I'm infamous for believing that SETH is false. So I see this as like, a path to showing SETH is false. Because in fact, like I could put a lot of different hypotheses up here and still get SETH is false. Some of which I'll be able to talk about, others I almost certainly won't get to. But if you don't believe, SETH, then you get so many more implications from assuming SETH. You get, in fact, non-uniform circuit complexity lower bounds from SETH, which you could possibly use to show something else down the line. Okay. Yeah, so I'm always like fighting with the contrapositive people. Well, I'm not fighting, I'm just sort of telling them this instead of the other thing because they don't believe SETH is false. So, yeah. So in particular, we get the following curious consequence. So if this disjointless function has one of these depth to neural net families with selection machine wires, I'll just write this over here just to make sure we have a sum of these thresholds, and we want to know if it can be made to the logn size. We're computing this disjointless thing. Then, in fact, for every k, CNF set with a linear number of clauses can be solved in square root of brute force search. Okay. And as a corollary, we get some win-win circuit complexity lower bounds. So either disjointness requires some exponential size circuits, or this embarrassingly large class exponential time of the NP oracle doesn't have whatever this is, linear size valiant series parallel circuits. And this really follows from either SETH is true, in which case this lower bound holds, or SETH is false, in which case we knew that even if you had like 1.9 at the end time for CNF set, then you get some kind of weird circuit lower bound consequence. I mean, valiant series parallel is just it's like a certain type of connectivity restriction on linear size circuits that Liz Valiant proposed in like 1975. And we embarrassingly don't know lower bounds even for super hard looking functions. Okay.
Why was it proposed? Why is it a reasonable notion of connected?
So it was a type of series parallel circuit where like you inductively build bigger circuits out of smaller ones by putting them in series or putting them in parallel. But it wasn't quite the series parallel definition, so that's why it's called valiant series parallel. But what's interesting is that these valiant series parallel circuits, like linear size ones, they can be represented by like a sub-exponential OR of KCNFs. So they can be, so you can do some kind of sparsification to them so that like not like they actually just become like a huge OR of CNF. So that's why like you can apply a set algorithm and say something about them. Yeah. But he was just proposing like some type of series parallel circuit for which he hoped we could prove a lower bound, but that was 50 years ago. So anyway, it's but it really boils down to understanding KSAT, which we still don't. Yeah, or at least on the level that, at least on this particular level, yeah. Does that make sense, or any other questions? No. I feel like that's as much as you need to know for this talk, but it's important to note. Yeah, it's like, I think it was like an invited talk at MFCS in 1975. Otherwise, it probably never been published or something, but yeah. There you go. Great. Right, so in order to prove these results, we will go through like a stronger notion than these sums of thresholds. Like instead of looking at circuits directly, we'll look at something that's actually a stronger notion, but it turns out to make the proofs like much easier to think about. Okay. So first we say a matrix is an equality matrix if there are some defining vectors u and v. Okay. So that for all I and j, the ij entry of M is 1 if and only if ui equals vj. Okay. So without all generality, we can think of u and v as being integers from like 1 to let's say 2n or something like that. Okay. Just to give some examples, okay, first of all, the identity matrix we can write with vectors like so. This is one of many possible representations, but there's other types of equality matrices you can get. You can get flowers like this, okay, with like these defining vectors and other nice things like this. So right there, they're sort of collecting together things like based on just the equality relation. Okay. Sometimes these are called blocky matrices because you could take like some block diagonal matrix of ones and then permute them. Yeah, so think they're also called like, I guess for various reasons, some P4 free matrix. They're avoiding like certain submatrices. They're also called fat matchings. Okay, I don't, whatever. Let's not shame our matrices. I prefer equality matrices. Okay. Yeah, because it's literally equality relation. Okay. So yeah. Okay. Great. Yeah, and actually, sort of recognizing whether something is an equality matrix is pretty easy to do. There's like a greedy linear time algorithm for doing that. Which you can think about if I start boring you, I guess, or you might already have figured it out. So what can we do with equality matrices? They help us understand thing number 2. Okay. So the first theorem is if the disjointness function on say 2n inputs as defined over there has a depth 2 neural net with W of n gates in the middle layer, then this disjointness matrix, the Sierpinski triangle matrix, can be represented by a linear combination of not too many equality matrices, actually n times W of n equality matrices. And so yeah, by Wn gates in the middle layer, I mean the number of wires sort of going into there. So, okay, so more generally, suppose I have some function from 2n bits to a bit. I can define naturally a 2 to the n by 2 to the n matrix, which splits the input into 2 parts and tells me in the 8th row and the bth column what FAB is. Then I can always get a linear combination for this M sub f using just equality matrices. Okay. So this is sort of the first type of theorem. So then you might say, oh, well, then maybe we could prove like lower bounds on the number of equality matrices that you need.
Sorry, but equality matrices are always symmetric, not? And these.
What do you mean? They're not always symmetric.
V1 can be equal to V2, but V1 is not equal to.
Yeah, they're not always symmetric. I gave you some symmetric ones, but like, yeah, they're not always symmetric though. Like, it's just,
But the second one is not
The middle
symmetrical.
one is
I threw in a lot of weird examples for you there. Yeah, it's, well, yeah,
Yeah, it's not the same vector. So
but, anyway.
Yeah, I was confused as well. It's not an equivalence relation. It's between UI and U and V.
yeah.
Yeah, they're just defined by whatever equality, so, okay. Right, all right, so let's see how to do this. So here's just a sketch of the proof, but I can give more detail as needed. So first, we show that there's a sum of greater than or equal to matrices. So these we will, let me see. So greater than or equal to matrix has like some defining vectors, and this thing is one if and only if UI is greater than or equal to Vj. So the obvious, I guess the natural definition that you might expect is one. So this is why I call it equality, because then I can say greater than or equal to, and then you don't have to think too much about it. Okay, so given a depth through neural net with W of n middle gates, let GI be one of these middle gates. This gate takes in two inputs and it checks a certain threshold value, right? So for all in-bit assignments A, let xai be like the contribution of like the x input if x was set to A, okay, to this threshold, okay, and y is t prime minus the contribution of the y variables. Okay, so I'm just sort of taking this thing, putting it here, sticking in A, taking this minus this thing, putting it here, sticking in A. All right. Then right, like xai is at least ybi if this threshold is supposed to fire 1. So now we can just define a Boolean matrix A sub I with these defining vectors, these x and y values, and then this thing will be 1 if and only if, when I stick in, so like the j, k, and should be 1, if when I stick in j and I stick in k, we have greater than or equal to, right? Pretty simple. So then a linear combination of these gives us the truth table of F, okay? Because F, could be represented as a sum of these threshold gates, each of which is captured by a particular matrix.
Does it matter if we're working in the model where it has to be 0 or 1 or just 0 non-zero? So if it's 0 non-zero, then this is just like you get a matrix where they have the same 0 pattern or something.
That's exactly what happens. Yeah. So then you would talk about whether M sub F has a non-zero zero representation. Yeah. Okay, so finally, we can convert each of these into a sum of n equality matrices. Okay, so let me show you. And so I have this greater than or equal to relation, and I want to sort of write it as some equality relations. So suppose I have like AV, which are m bits. Okay, so then I'll say like, okay, so A is greater than equal to B if and only if A equals B, or they're equal in the first, say, m-1 bits, and AM is 1, and BM is 0, okay, or they're equal in, like, say, the first I bits, and the I plus 1th bit of A is 1, the I plus 1th bit of B is 0, and so we just keep taking 4s, and eventually we just get to like A1 is 1 and B1 is 0. So it's just sort of finding the first bit in which they differ and making sure that A is 1 and B is 0 in that bit. Okay, just sort of writing this thing out. Okay, so some observations to make about this. At most, one of these conditions in the OR of things can be true, right? Like there is a first bit in which they differ. So I could really just write this as like a sum. Like even if these were giving me, even if I thought of these as like functions giving me 0, 1 values over the integers, I could still write it as a sum. They're completely disjoint. Okay. And then the other observation is that each of these can be expressed by equality matrices. So like if I have like this vector of like say A1s and ANs and B1s through BNs, and this is defining some greater than or equal to matrix, I can write each of these as equality matrices. Like this one is obvious, it's literally the same vectors. But the others are just a matter of sort of perturbing the bits in the defining entries for them. Okay. So each one of these can be represented as a separate equality matrix. So like, this and of things, like actually I don't need very much for that at all. Like I can just have like a single value for when this thing is 1 and when this thing is 0, like just have like a single defined value for them. And then if this thing is 0, then I'll have another value that this thing can never be equal to. And if this thing is 1, I'll have another value that this thing can't be equal to.
So are you implicitly using that XA has only n bits?
Yes. So here, okay. Actually, I could have started with arbitrary weights, but after, like if I sort the weights, like in a particular like column or whatever, if I sort of sort all the weights and replace them by their ranks in sorted order, then I will preserve this. So that's a good point. So let's suppose I have an arbitrary greater than or equal to matrix, right? And like with arbitrary like defining weights. If I take all those numbers and I sort them and then replace and then take the ith one and say its number is I, then the greater than or equal to is preserved completely. But now I only have like two n different weights. So yeah, I do that and then I make the equality matrices. Great. Yeah, good point. Yeah. Good point. Yes.
So, if you are given a greater or equal than matrix, can you efficiently recover the weights? Like propose one one valid weights that produce this greater or equal than matrix.
Oh, so given a greater than or equal to matrix, so just given the 0, 1 matrix, say it's great, and someone promises you it's greater than or equal to?
Well, I guess checking whether that is a greater or equal than matrix should be efficient. But I'm saying you need to match that format. Like it comes from the threshold function.
Oh, you want to know whether given a greater than or equal to matrix, does it come from a threshold function?
Yes.
Oh, I'm not sure. I'm not exactly sure. I haven't thought of this question. It's whether it fits this kind of format, whether there is a threshold that models it. Yeah, could be. I haven't thought about this, but
No problem.
yeah. I mean, in general, if I gave you a matrix and I want to know whether it's a linear combination of greater than or equal to matrices, like say I make your question slightly more complicated, then this is essentially like trying to solve like MCSP for sum of threshold circuits or whatever.
Yes. Yes.
Which we don't know how to do and probably hard. I don't know. What do you think?
All right.
Yeah, but yeah, for a single one, yeah, it's probably possible. But yeah. Yeah, I think you can probably do it. Great. So can we prove lower bounds using equality matrices? Because, right, we have this theorem. So the idea is to exploit the contrapositive, right? To sort of show here's some functions, maybe disjoint this function requires like a bunch of these simple matrices in order to compute them. But the greatest barrier to lower bounds is upper bounds, it turns out. So this matrix M sub m actually has very small linear combinations for small n. I mean, I'm not saying that SETH is false, but yeah, like when we study like small values of n, the ones that we can fit the problem, you know, on a computer and run a SAT solver to try to refute a hypothesis about SAT, then we can find some things. So first for 2 to the 2 by 2 to the 2 disjointness, this is one of the many possible things you can do. You can take this equality matrix and that equality matrix and subtract them and get your nice little guy. So this only takes 2, but okay, that's a very small case. For 2 to the 4 by 2 to the 4 disjointness, here's like one of many different linear combinations. There's the thing is the space of feasible solutions is so large that it's hard for me to even know what kind of things to impose. Like here, I impose that like, okay, all 4 quadrants here are equal. I think I impose that like these 2 are the same, you know, things like that, like, you know, restrictions like that. And you know, this gives you exactly what you want, and it only takes 4. Yeah, like, and for 2 to the 5 by 2 to the 5, you can, you know, so this one has got like the same quadrant 4 times. There's a yeah, I guess these 2 are the same as well, but yeah, I guess yeah, these 2 are also the same. Okay, yeah, so I was imposing more symmetry there. Then like you subtract something, you add back, you subtract another thing. Yeah, and then you subtract one more thing, and you get this non-zero zero representation. So this light blue is 0, and these are all like, you know, some of them are negative and some of them are positive values, which are capturing exactly disjointments.
Were all of the other sums true 0, 1 matrices?
Oh, the ones, the previous ones?
More than smaller.
Yeah, the previous ones, yeah. But I should stress that like, that for each of these things I'm showing you, there's like hundreds of thousands of other ones with the same number of matrices that I also found. These are some random cherry-picked ones. Like, I mean, yeah, and many of them are structured, you know, but obviously I was studying to try to see, okay, is there some inductive pattern that I can use to like extrapolate and get something more? Yeah, this only takes 5 for 2 to the 5 by 2 to the 5. And also for 2 to the 6 by 2 to the 6, okay, just slash these guys. They sum to this, and there's 6. So, I mean, the natural conjecture, I guess, is that actually it only takes D matrices to get 2 to the D by 2 to the D disjointness, I guess, given the data. But yeah, that, like, you know, if you believe the other theorems, which I'm going to prove, that would completely obliterate the not only SETH, but the orthogonal vectors conjecture.
Sorry, that's plausible as far as anyone knows? Like, it's not like.
What do you mean?
Sorry, I meant that somehow I was picturing that the best you could do was some 2 to the n over 2, like you were looking for. Like,
oh yeah, so that this 2 to the n over 2 is an artifact of the reduction. Yeah, so this is talking, yeah, so it takes a few steps to get to the 2 to the n over 2. So what's actually happening is in the algorithm that I stated, there was a 2 to the n over 2 plus little o of n, okay? And what I'm actually talking about is a little o of n term. So I'm saying like this, as long as that's, because I was saying if you have 2 little o of n, whatever, equality rank, you know, you can think of this as equality rank, the minimum number of equality matrices that sum to disjointness. So disjointness of 2 to the n by 2 to the n. So if you have that, then you get this time for SETH. So yeah, I don't know how to improve this thing, even if I have like, even if this equality rank is actually n.
I guess I should ask, is there any lower bound known on the quality rank of disjoint?
I think you can probably prove like something like omega n. Yeah, I don't think that's hard. But yeah, I like there isn't anything ruling out the fact, like the idea that 2 to the 7 by 2 to the 7 would have 7 and so on. I mean, the only impediment is like that the set solver just doesn't terminate. I mean, that's not, like this, yeah. So this is all found with like, well, I used a combination of different things, but these were the fastest was like this solver, this open source solver by Microsoft called C3.
Do you know you can't do it with fewer than D for any of these examples?
So I think that like you can probably I think yeah, does it even stop and tell me no? Like the only way I would prove it is by the SAT solver literally telling me no or whatever. But in the most general case, I'm not sure that I can get it to even stop. But certainly like natural special cases, it does seem like I would conjecture that D is a lower bound for 2 to the D by 2 to the D. Like, yeah, that for equality matrices you can't do better. But I don't know if that's true. Yeah.
So if the 2 to the little n is the rank, like the equality rank of disjoint matrix,
Yes.
then why do you need some exponential lower bound to rule out SETH? Like it seems if the equality rank is 2 to the like 0.1 n, it will still be much faster than brute force, right?
Yeah. Well, there's some other stuff going on. Like so that would rule out like yeah, 2 to the less than n over 2 like
Yeah.
quality rank in a uniform setting. But remember, there's like a non-uniform connection that we have to make.
Okay.
Right. So that's but yeah, I mean you could probably have like for sure, like I just didn't specify the epsilon. But in one of the cases you definitely have 2 to the epsilon in lower bound, whatever some epsilon. Yeah. But there is a sort of non-uniform bridge that we have to gap it as well. Yeah. Right. So what? Okay. Well, suppose for all epsilon and sufficiently large n, m sub n can be represented by a linear combination to the epsilon n equality matrices, then strong EKH is still false. Okay. So I mean, right? I was just saying, if you have like these circuits, then SETH is false. But in fact, it suffices to just have a linear combination of equality matrices, which is potentially much more expressive. And in fact, like you can come up with equality matrices that are like sums of equality matrices that cannot be captured, like by at least by a small finite sums of thresholds. Like there are cases where I can like I don't think that let's say if I go back to this thing with like 2 to the D by 2 to the D disjointness, that's a sum of D equality matrices. I highly doubt something like that is true for here. Like I highly doubt you can even get D times N in the fan-in here and compute disjointness. So equality matrices are much more expressive. You can we show that how you can embed right like thresholds into equality matrices, but equality matrices are much more powerful. Right, and so in fact, a stronger conjecture, the orthogonal vectors conjecture, would be false. Maybe I could take a break for 10 minutes here, and you can stare at this, and then I'll explain what it means. Yeah, for now.
So Ryan, if let's say instead of disjointness, I have some other problem which has like a recursive structure, like then I mean a disjointness makes sense, it corresponds to OV, but let's say I have another probability distribution recursive structure, should also work for whatever the analysis OV is there?
Yes, this is a much more general framework than just disjointness. Yeah, disjointness happens to be the function that you're computing, like among these pairs. Yeah. paper, I call it like, given a matrix M, we define M satisfying pair problem or whatever.
I see.
Where, yeah, like I give you, because, right, you can think of this as, I give you an N by N submatrix of this thing, and I want to know, like, does it contain a one, basically?
And your thing works like whenever you look at the Kronecker power or something like that, or it's even more general? Or
Yeah. So the Kronecker power stuff is to show that, is to get the uniform and non-uniform connection.
okay.
Yeah. Let me check and make sure I have enough notes to like convince everybody of the Kronecker power thing.
Yes, so we build the tide.
And I guess
What was the question about the context?
I was just asking. So I
So
was asking how much more general is the connection? Like if you have a recursive composition of a matrix, this thing you and whatever you get this quality rank thing, this thing can be faster algorithm for the corresponding computational problem. And then you're saying yes, and I was wondering what the
זה המוטיבציה שלי, אבל תגובה למה שג'ון דיבר, והיית אתה רצה על משפט אורנשטיין. המחקר שדיברנו אישית, ויש להם את האלקטרוסיות של הבסיס, זה מאוד. בהקשר של שאלה המקומית של פורנאים,
Fairly simple. And in a hidden way, it is using the same Wronski.
מישהי פה אמרה שהוא נראה כמו אימון. סתם לא,
Yes, but the trick out is the dimension of the line subspace. The line subspace is always there because it's a linear space. The key thing is that it's of constant dimension.
Yes.
It's of dimensions that you would have guessed directly looking at, like the fact that list lies in a small dimension space. We saw last time. Even though that wasn't clear, I think that has been further simplified. Extension can show that to be comes with a that's for the one more if you just want to, if you want to know then the proof that I showed you last time, just looking at S linearly independent or S plus 1 linearly independent, you reach a contradiction that not all of these could. That's even easier than doing interpolation. You don't need to do interpolation to interpolation itself. There's just a fact about Wronski and polynomials. And then Kurosawa's algorithm gives you an algorithm to find the basis for that. Solve the linear system that he builds. But it's a beautiful algorithm. Even if I told you just the combinatorial result first and asked you to come up with an algorithm, it's not obvious to me how to come up with it. It's not a very, but here when you try to solve a linear system, you automatically end up with yeah, but yes, but the fact that you're solving that particular linear system is the novelty. Why would you set up that linear system?
This is linearly not the y.
Or even do interpolation. Like, let us flip the timeline. In the timeline, this interpolation business was set up first. Yeah, I understand. But yes, let's say interpolation was not in the time. We directly proved the combinatorial result that the list is small. List dimension is small. That you can prove just using Wronski. There's no algorithmic fucking anymore.
Right. Imply is the best thing. You might need to enumerate over all this time.
That's very cool.
Yes.
That's not easy. This particular algorithm, like now it is kind of, it still does not feel the most natural one. I'm not trying to challenge you that we should have something else, but
הגעת מההתחלה?
I
לא, הגעתי
think there's a lot of novelty.
איפור, אבל למזלי הוא דיבר
It's
כבר על
simple
הדברים
because of the historical
גם
development.
בקולוקטים של זה, אז היה לי ברור כאילו,
Yes,
אולי
let's
אנחנו
simple.
חוזרים לפעמים
Yeah.
את ה-win-win situation הזאת של מה.
כן, כן.
מרצה טוב וזה, זה דוקומנט כאילו, יש משהו, כאילו מרגישים את היצירתי. גם סיזיפי, כאילו, הרצון להבין, ולהסכים, משהו רוצה להבין. אבל גם רואים שיש המון שבילים של יצירתיות שם. אני מבין גם שזה פרויקט, לא רוצה להגיד, זה פרויקט חייב.
כן. כאילו, הכיוון שם. סינגל הנד. אתה קופץ בשבילו?
כן, בשבילו, לא, ולקחת את זה.
לא.
כשאני קצת פחות זזום תורד. זה גם כל שעה. גם ככה עוד שעה שקט, ואני יכול לשמוע את ההצעה. זה חמור. כן, היה רוח דבר, צער בידו?
Right.
כי יש לך
Right.
Yes.
Is it possible to take a representation
לא,
of
צער
NK with like some small number of equality matrices and then test it on that representation?
Yeah, that's basically what we do. Yes.
Okay.
Yeah, the Kronecker
Yeah.
power thing was like foreshadowing. Yeah.
So that gets you to the epsilon n, right?
If you believe this conjecture that M sub D has like D equality, right? Like, yeah, then you.
Oh, because you want to the epsilon n for all epsilon.
Yeah, for every tiny epsilon.
Okay.
Yeah. So you already get something.
Okay.
Yeah, you already get something, right? By taking.
So you really wanted some epsilon.
Yeah.
בגלל שיש הרבה דברים מאוד רוק. אתה לא חסת
זה מטוטלת.
אין בסצנה של המוזיאון.
כן, לא נראה לי שכבר.
גם בוויטני
אנשים כאילו של אומנות הזה, זה כאילו, עכשיו מאוד הטרנד.
So Ryan, I guess if we're making a non-uniform circuit, convert it into uniform circuit with asymptotic Is that true?
Sorry. What?
Let's say you have a non-uniform
כן.
circuit or matrix mult. It has whatever the omega for that
זה
circuit
גם
is.
מעניין, אתה רואה הרבה יותר...
Yeah.
You can make it a uniform one just by
You can get a uniform one for like all large values of n, but you got to hard code the non-uniform guy. Yeah.
But so omega non-uniform is the same as omega uniform. Is that true?
Oh, usually it's just defined this way. Usually people don't even like distinguish between. Yeah, because they say they compute the rank of matrix multiplicative, which is a non-uniform motion, and they argue there is a matrix mult algorithm. Yeah.
Are there a problem? Can such let's say a problem with this property, kind of uniform property or whatever. Because there are problems with this property that are outside.
לא, לגמרי.
What's the question? It's like somehow it's like
זה מורכב, אין נכון.
this is the asymptotic complexity of
לא יודע אם זה
non-trivial uniform algorithms.
Yeah, I mean, people don't know this. Like, this is sort of like what conjectures about de-randomization making. He needs exponential size circuits. Is this what you?
Okay, I'm asking for what problems can we prove currently that asymptotic and non-asymptotic algorithms? Uniform and non-uniform algorithms that asymptotically
לא, לפעמים זה לא בקטע הישראלי.
Like so matrix mult is a problem like this, right?
Yeah.
I guess there must be, right?
Yeah, there. Yeah.
למה שהתחילה?
Yeah, it's, but like, for each one, you've got to define like the right computational model along with the problem, but yeah.
Okay.
Yeah, I don't know of like other, certainly not an example more natural than that. I need to look at something. Let's see. Oh God.
I was kidnapped by idiots. זה באמת מדהים. לקרוא וזה בדיוק נוגע בכל הנקודות האלה, לכל הכיוון.
כן.
Right, so if I have a linear combination of select exponentially many equality matrices computing disjointness, I'm going to show that the orthogonal vectors conjecture is false. So the problem is I give you n Boolean vectors in some C log n dimensions, and think of C as maybe some fixed constant parameter, but very, very large. You can find an orthogonal pair if one exists in nearly linear time in the number of vectors. So maybe it's what we're sort of thinking about what kinds of algorithms are kind of natural ones that we can get for this OB problem. So the obvious algorithm is to just try all possible pairs, and that will give us n squared times log n. But you can also do things if the dimension is not too large. You can get algorithms like, for example, for dimension d, you can get something like to the d plus n. So like if the dimension d were like less than 2 log n, then you can get a slightly faster algorithm. What's the best way to show how this works? Well, one way to think about it is, let's say I want to find a u and a v so that these are orthogonal, so they're disjoint. By flipping the bits on, so first of all, I can think of this as having like a set of red vectors and a set of blue vectors, and I want to find a red pair and a blue pair such that this is true. So first I can assume this, and the way I can do it is by extending, so take all the vectors, over here and over here, then extending this so that like I have a 1, 0 over here and a 0, 1 here, just to show you that like I could have a like if I had a red blue thing, I could just combine them all into one if I wanted. So let's say I have red vectors and blue vectors. I want to know there's a red blue pair that makes them orthogonal. I could flip the bits on this side and now ask whether there's a set that's red that's contained in a set that's blue. But if I flip if I take the complements on the blue side, right? So now I'm asking whether the set S is contained in a set that's blue. Okay, and so now like I have like a bunch of sets like S1, S2, Sn, and I have another bunch of sets. And I want to know like let's say I place them down in the Boolean hypercube somewhere as points. Okay, then I want to know if there's a path. Like if I direct the path so that vectors that add flip a 0 to a 1 like in that direction. So like yeah. So in like the monotone like directed hypercube. So now I just want to know if there's a path from like some Si to some Tj there. Okay, which I can do by just simply doing some dynamic program starting from like the all zeros and then sort of moving up. Like if I will just mark just keep marking nodes of the hypercube whenever a red node, has a path to it. And if I ever have a red node, like mark a blue node, I'm done. So this is how I get to the d plus n. This is one way of getting to the d plus n. It takes n time to sort of place them in the hypercube, and then it takes like, say, d times 2 to the d time to sort of do this dynamic programming, walking through all the nodes, like starting from all zeros, then all the vectors with Hamming weight 1, Hamming weight 2, and so on. Okay, so this is one way to get this thing. Yeah, and so this is why, the problem, we set the C to be arbitrarily large. Well, another reason we set C to be arbitrarily large is that it will capture a CNF set for one, and there's another algorithm which I would be remiss to omit because it's my own algorithm that runs in this much time. So like for C log n dimensions, you can always improve a little bit over n squared, okay? By like a little bit. This is work with Amir and Hotching from a long time ago. But then, as C gets larger and larger, this gets closer and closer to n squared. It's quite similar, probably not without coincidence, to the case of k-sat, where like for every fixed constant k, there's a k-sat algorithm which runs in less than 2 to the n time. But if I let k grow arbitrarily, then the best algorithm I know is basically like 2 to the n. Okay. So, but if this, one thing I would add on top of this, like if this conjecture about the equality rank of disjointness was true, that like disjointness of 2 to the n by 2 to the n really had like a sum of n equality matrices, then not only would OV be false in this case, it would even be false in like in the case where the dimensions like were even like slightly polynomial, like in the epsilon. Like it would be, you could still have a subquadratic algorithm. So,
And Ryan, what was that, like, I guess over like F2 or something, it's false or something? Or like,
yeah, it's great. So let's suppose my inner product function is not over the integers, but modulo 2. Yeah, then this conjecture is false with a nice randomized algorithm. There's also a deterministic one, but it's more complicated, and for whatever reason, I still haven't written it up completely.
That's over, is it specific to F2 or like
yeah, over FP, you can get, okay, I've run out of board. Let me just, yeah, over FP, you can get something like, bless you, n times e to the p minus 1. This was actually work with Hotching a long time ago. So like, so in other words, like if you're computing whether there exists UV so that UV is inner product is 0 mod p. But yeah, so yeah, how does this work? Well, let's look at the case of F2. Maybe I will leave well, you can figure out the other case, I think, if I show you the case of F2. So what do we want to do? We've got like, let's say we're in this sort of red-blue vectors case where I've got some in red vectors and in blue vectors, and I want to know there's a red-blue pair, it's orthogonal. So this is like, yeah, so this D is the dimension. So I'm looking at some n by d by n matrix product, right? And I want to know if it contains a 0 entry or not. This is the orthogonal vectors problem. But I'm working over F2, right? So there's only one other possibility over F2. If it's not 0, it must be 1. So what I'm really checking is whether this thing is all ones, right? Right? Well, that I can do with a matrix null checker. So there's a matrix, like this actually came up in Orr's talk. I think it's like a matrix null checker. Yeah, you can check, because like I have like a fixed matrix here. I have 2 input matrices. I want to know if they're equal. Well, what I can do is to take a random vector v over 0, 1 to the n, or this is n by n. Now, because this is so simple, it's just all ones matrix, I can compute the matrix vector product like immediately. Like I don't have to actually take n squared time for that, right? And over here, I'll multiply by this one, right? And this I can do in about n times d time. Do this one, then do this one, right? So like do it like that. And this will catch, if they're not equal with probability like a half, and then I just repeat it. Okay, so mod 2, this is pretty easy. Mod p, you use the fact that, okay, there's p minus 1 other values. Instead of having one other value, there's p minus 1. So then you use Fermat's little theorem. So like to extend the dimension to d to the p minus 1, and to sort of like just take the inner product to the p minus 1 and like subtract 1 to like flip it. Okay? So now you're checking whether like it's all zeros. Right, because like here we're just exploring the fact that if it's not 0, there's one other value. But if there's like 2 other values, then you can like have a polynomial which vanishes on those instead. Yeah. So yes, it's an interesting special case that like is very immediately solved by things that we know. Yeah. Great. Right. So first, let me show you how you get a faster SETH algorithm from orthogonal vectors. Right. So this is an important point, and it's a bit strange because it actually says in a certain sense orthogonal vectors is harder than SETH, but like only in this really weird sense because one's a quadratic time problem and one's NP hard. So only this weird sense of time complexity, like improving the time complexity of orthogonal vectors is harder than improving the time complexity of SETH. This is what's one of these remarkable things about fine-grained complexities, that you end up showing problems harder than others because you're so focused on the time complexity and not about like anything else. Right. So a theorem proved way long time ago is that orthogonal vectors with n vectors and order log n dimensions. I don't know why that rendered weird. Okay, this is an implication. Okay, if it's in n2 minus epsilon time, then SAT with n variables and order n clauses is in to the little n minus epsilon n over 2 time. So any subquadratic time algorithm for orthogonal vectors immediately gives you something sub 2 to the n for SETH. So the proof is pretty simple, but we use the fact that without loss of generality, like here, like the order n clause case is the hard case. So if you're given a CNF with n variables and m clauses, we're going to construct a set of 2 to the n over 2 plus 1 vectors in n plus 2 dimensions, so that the formula is satisfiable if and only if the set has an orthogonal pair. Okay, and this is a very standard idea in fine-grained complexity. You have some hard problem you want to improve over a brute force for, so you split the search space into like these different parts. And you define some polynomial time problem, which is like the problem of merging together parts to find a solution. So we split the n variables into 2 parts, P1 and P2, that have about n over 2 variables each. Okay. And we make vectors for all the assignments in the part. So you can imagine we have red vectors, 2 to the n over 2 red vectors for P1 and 2 to the n over 2 blue vectors for P2. And so for all assignments A and P1, we do this little encoding where in the n plus 1 and n plus 2 component, we put 1, 0. And in P2, we put 0, 1. And for all I, so ranging through the possible clauses, we make the ith component 1 if the assignment A, the partial assignment A, doesn't satisfy the ith clause. Okay, so it might not satisfy the ith clause because it simply doesn't assign any of the variables. Or the variables it assigns, it always, the variables it does assign, it assigns them to false, right? If it doesn't set a variable to true, then it doesn't satisfy. Okay, so we're just asking, okay, does this partial assignment satisfy? We put a 1 if it doesn't satisfy. Okay, And then we do analogous thing for the things in P2, except we swap the 0 and 1. This is just to enforce that, if we union all these things together to get an orthogonal pair, we've got to pick a red one and a blue one. That's only part of like the 0, 1 and 1, 0 thing. Okay. And so, so it's not hard to see that orthogonal pairs now directly correspond to full satisfying assignments, right? Because if it's a full satisfying assignment, then each one of the clauses C1 through Cn is satisfied by either the partial assignment from the first part or the partial assignment from the second part, right? Some variable's got to be set to true. In which case, in every single I, at least one of these is going to be 0, right? So they'll be orthogonal. On the other hand, if an assignment is falsifying, then there is some coordinate in which they're both 1, like neither partial assignment does. Okay. Is it clear? So it's like we took the search space and we split it into these two parts, and now the OV problem is kind of encoding the problem of like taking two partial assignments and patching them together to get a full satisfying assignment. Yes.
So if it's not a 1, you can assign it to be a 0.
Yes.
So this is like a disjointness problem. It's like a
It's
special.
exactly a disjointness problem. Yeah. Yeah. And this is no. Yeah. I mean, maybe it should just be called disjoint vectors or something for the purpose. Yeah. Yeah. And and the disjointness function is exactly what we're computing. Yeah. Absolutely. Okay. So we have this instance of order to the n over 2 vectors. So if we get a subquadratic time algorithm, then we actually solve SAT in sub to the n time. We somehow avoided exhaustive search over all the things in P1 and P2. Okay. Yes.
So this reduction also works in a finite field, right? Like if you modulo P, then
If you work modulo P where P is large enough, right? It needs to be like at least.
No, I'm saying even for small P, then you are checking whether there is an assignment that satisfies, let's say, like even number of clauses.
Yeah.
Like 0 modulo 3
Yeah.
of clauses. And then you have a better algorithm.
Yeah.
So that will translate to like like better than 2 to the n. I think it's 2 to the n over 2 runtime.
Yeah. But you can even get polynomial time for those things. Because let's say I have a polynomial of fixed degree with like a fixed sparsity in F2, and I want to know like does it have an assignment which is 0?
Yeah.
Right? I can just apply Schwarzschild directly.
Right.
Yeah. But so you can actually get a randomized polynomial time algorithm directly from those things. But it's instructive to think about what happens to this reduction whenever you run these other algorithms instead. Yeah. But in that case, there's like a more direct solution. Good. Very good. Let's see. Great. So, right. So now I want to describe like how we get algorithms from these equality matrix representations. Right, we were just saying, okay, I ran the SAT solver and I got for 2 to the 6 by 2 to the 6 disjointness 6 equality matrices. But like, how could I use that? How could I get an algorithm from that? And these equality matrices could be anything. And suppose like I proved that the thing existed, for infinitely many R, but like I couldn't even necessarily get my hands on it. Like maybe I use some extremely indirect existence argument. Even so, no matter how that thing exists, if it exists, then given n Boolean vectors in d dimensions, we can find an orthogonal pair faster. And how much faster depends on the number of equality matrices we use and how big the disjointness was. Okay. So we get this n times r to the d over k.
Are you going to use the tensorization now?
Yeah, it's exactly. Yeah, exactly. So, I don't write something on the board unless it's going to get used in the second act or whatever. Okay. Right. Yeah, exactly. So, but what's cool is a non-uniform upper bound implies a uniform algorithm. But I should say that this is standard in the design of matrix multiplication algorithms where, you show, like they all implicitly show, at least that's the standard way it shows, that the ones that are, algebraic, based on Strassen and so on, that get truly subcubic, they just show that the rank of K by K matrix mult is, something small in some sense. And then you use the fact that like I can apply this algorithm sort of like recursively at every level of recursion and then get an algorithm that works for all n larger than this K. And this is very analogous to what we're going to do here. So if you have this non-uniform upper bound disjointness, you can get a uniformly computable linear combination of equality matrices of this many for 2 to the d by 2 to the d disjointness. That's the idea. And then once you've got this like uniformly computable linear combination of this many, then I can sort of break down the orthogonal vectors problem into into basically this many instances, each of which can be evaluated in this much time. So this is the super high level idea that I'm going to go in detail about. But one thing I want to point out, a corollary of this theorem is that, just plugging in, 6 for K and R, we do get like some sort of simple algorithm. This one that I was talking about, that here, this is actually based on fast rectangular matrix mode. So it's like, it's not implementable really. But like this sort of thing is actually very implementable. And Josh Allman, my former student, has been plugging away. He found some new ways to represent things. And I think this is now down to 1.17 or something to the D. But I think, yeah.
Is this potentially useful for being a SETH solver?
Oh, for being a SAT solver in itself.
Solving a SETH solver?
Yeah, perhaps. I mean, on the other hand, like we're only improving over, 2 to the n. So like it would be a SAT solver for, the ones which make all the other SAT solvers die. Yeah. It is. Yeah. Orthogonal vectors in itself is an interesting problem. There's like a whole equivalence class for it as well, which is like, trying to, like, for example, approximately compute the maximum inner product of 2 vectors in this collection. Like, depending on how you define this, you can get some equivalence with OV. So there's a collection of like vector problems, like in like slightly higher dimensions, like order logn dimensions, which if you could solve OV faster, you could solve all these faster as well. So,
but those are problems that are interesting for complexity theorists, or SETH solver is of interest broadly.
Yes. I mean, I think finding like, proximately closest pairs and finding things with large inner product are of interest practically to like some people. Yeah. So that's what I'm saying is that like probably the SAT solver thing, because it's got this 2n/2 overhead sitting there, it's probably not practical. But I would guess that like a very practical OV algorithm could actually be really useful for like high dimensional like search, like slightly high, like order logn dimensional or like high dimensional search like that. Yes.
Does this give any better worst case SAT algorithm for any K? Like by just plugging this in?
Does this give? Not quite. I mean, it just gives a weird algorithm. Okay, because like from our reduction, this capital N is, let me just write it down. So this capital N is like to the little n over 2, where that's the number of variables, right? And then this 1.35 is like to the number of clauses. Okay. This is weird. I mean, like people don't typically study these kind of things. But yeah, the point is that it is, kind of an alternative type algorithm. Yeah, I mean, that's what kind of makes this this one over here appealing, is that if you apply this algorithm, you essentially get like to that reduction, you sort of recover the best known CNF set algorithm for sparse instances, for like a sparse number of clauses. Remember this C is like, C times like n, where n is the number of clauses. Like if we apply, if we go back to like CNF set, we get like something like log C for CN clauses, which sort of matches the best known CNF set algorithms. Yeah, I didn't really talk about the best known CNF set algorithms, but I mean, if if I run out of slides or material, we can also talk. Yeah. Great. Right, and some corollary is okay. If I plug in like R as like 2 to the epsilon n, and I have like large n, then basically this overhead can be made as small as we want. This overhead can be made like 2 to the epsilon n, where n is the number of variables, like in, well, I guess in like the CNF set instance. But for orthogonal vectors, we can make this like capital N to the little one. For dimension, I guess this should be a capital N there. So let me show you how to prove this. Right, so I'm going to kind of do two different things in this theorem, right? Because one, I have to say, okay, how to go from a non-uniform linear combination to like a uniformly computable thing. And then I have to tell you how to get an algorithm. So, but the idea here is to reduce OV to computing R to the D over K into some nearly linear time problem. So actually, I kind of stated the theorem a little bit differently here, because I think this is a better starting point. It's a little bit easier to wrap your head around. So here we're saying, suppose there's some K so that this disjointness matrix can be exactly represented by a linear combination. So now, in other words, when I sum everything up, I get exactly the 0, 1 disjointness matrix, okay? But then, in fact, in that case, we can count the number of orthogonal pairs, which is a presumably harder problem. Okay, so this is like sharp OV, counting OV instances. But the reduction is a little bit easier to see. Like both steps of the proof are easier to see in this case. So recall we had this representation of M sub D as a D over kth Kronecker power of M sub K. It's just by taking the and things. So, okay, our hypothesis shows us that this M sub D can be represented as some linear combination of equality matrices, E1 through ER, right? And so we can plug in this, right? We basically substitute M sub K for this. That's all we're doing here by our hypothesis that there is some linear combination for M sub K. Okay. And then when we expand this thing out in sort of a natural way, like if we expand out like this Kronecker power of a sum of our matrices into, a sum, we can expand to a sum of R to the D over K matrices. Each one is just, this sort of Kronecker product of some equality matrices. Okay? But equality matrices are closed under Kronecker product. Like, right, if I have two equality matrices and I compute like their and, this is also an equality. Component-wise and, this is also equality matrix. Right? Do you see why you got just like concatenate the defining vectors, like each of the defining vectors, like for the two? Because now like first halves need to be equal and second halves need to be equal. So like it's a very simple operation. We'll just I can take the and of two equality matrices and get a new equality matrix. Is it okay? Yeah, okay. So, and the point is that like if K was like fixed, right? Then in fact, like each of these equality matrices could be computed efficiently given like, an index telling me which one I want. Right? So if I want to know, let's say I index, like I have an I ranging from 1 to R to the D over K, right? And I want to know what's the ith equality matrix. right? I can just sort of look up, like, because I have like some D over K tuple with like entries from 1 to R. Like I can look up what this equality, what the corresponding equality matrix is, because it's like just picking out one from each of these D over K tuples and then just like literally concatenating all their entries together. So the point of saying all this is that like this is an extremely uniformly computable thing. If K is like fixed and D is something very large, I can actually compute any entry from one of these matrices in like polynomial in D time, basically. Okay. So the point is that it becomes like a uniformly computable representation. Okay. So not only can this thing be represented by a linear combination of R to D over K equality matrices, but each entry of any particular matrix I want can be computed in poly D time. So again, think of K as fixed and D as like growing very big. And I just want to know, like, so I can write more if you want. Or we can just think about it. We can like have a pause for reflection or whatever. I mean, but yeah, it really is just a matter of like this equality matrix is like defined by like taking the defining vectors here, the defining vectors here and here and here, and just literally concatenating like all their like component wise, like their entries together. And now it's the end of everything. Okay. So that makes it like very, very simple. And these coefficients, right, I have to like sort of take the coefficients along with them. This is like a product of a small number of numbers. Yeah. Okay, so now I have this uniformly computable linear combination of equality matrices. So now I want to like somehow use this to compute the disjointness predicate. And sort of the key observation is if I give you in red and in blue vectors to test for orthogonality, this is basically equivalent to just testing, I want to test whether some n by n submatrix of the disjointness matrix contains a 1. Right? I mean, I guess I was, let's see. I was already doing that somewhere. Oh yeah, forget it. Right. So like here I was just testing, whether this thing is all ones. Like here I can think of, let's say I'm computing orthogonal vectors on D dimensions. Right, this is just equivalent to saying I have n red vectors, I have n blue vectors. I want to know like if there's some matrix contains a 1 or not. Right? That's it. That's all I want to know. And so I'm going to use this equality matrix representation to reduce the search for a 1, in this case, actually counting the number of 1s in the submatrix, to like some very, very simple problems which can be solved by sorting, actually. So, so I have like these R to the D over K equality matrices representing disjointness. I fixed one of them that has some defining vectors for them. But remember, I can uniformly compute any entry of the defining vectors that I want, like in poly D time. So I'm not actually storing these things. That'd be 2 to the D, right, by themselves. But I can implicitly access them however I want. So I look up the red vectors in U, right? So there's right, because I'm trying to compute some submatrix. So I look up, for each of the red vectors, what their number or entry is in the defining vector U in poly D time for each one, and the corresponding ones in V, right? So now what do I want to know? So I've got an equality matrix and I want to count the number of 1s in some subrectangle, right? So I have n red numbers and n blue numbers. I just want to count how many red-blue pairs are equal. Well, I can do this by simply sorting the whole list. Okay, and then scanning through it, and then for each sort of equivalence class of things which are equal, right? I can check how many red-blue pairs are equal. Just sort of sorting by the number and leaving, letting it carry around the color, the red or blue color as it goes. So for each fixed number, I just count the number of things that are red, both red and blue with that number. That's it.
What, sorting by?
The numbers. Like the numbers and the equality matrix.
That you get is ordered by what?
What? So there's equality matrices, right? Like so there are these equality matrices that are like defined by like some vectors, right? And right, so in our case, we have some equality matrix. We're going through a whole bunch of equality matrices, like r to the d over k, right? And each one is a 2 to the d by 2 to the d equality matrix, right? So what I do is I have like some red vectors, let's say u1 through un, and blue vectors v1 through vn. I look them up because this 2 to the d, right? So these components are indexed by d-bit vectors. Right? So I just look them up, and these are some numbers. These are some numbers defining an equality matrix, right? So I look up the numbers, and I want like to know whether or not there's a 1, or count the number of ones in some subrectangle of an equality matrix. I just need to know like how many red-blue pairs are equal, because that's what makes something a 1 in an equality matrix, whether the red thing is equal to the blue thing.
These A and B are the vectors that define the equality.
Yeah, these are the components. Like, so this is like, so just think of this as like defining vectors for some equality matrix.
Or U
So
and
you
V.
can sort by anything? Like you're just sorting, you're thinking of the
Like all you really want to do is arrange them into equivalence classes. I mean, you could use union find or something if you really wanted.
okay.
Like you just like maybe it was a sorting thing, because yeah, I just want all the numbers that are equal to be in one place. That's all.
Just when you say sorting, you're saying you're thinking of these binary strings as numbers in a binary representation.
Yeah. These things here. Yeah. So I think of them as numbers.
Okay.
Yeah, and I want to know whether two numbers are equal or not. Yeah, but all I really want is just to collect the ones that are equal. Like if all of these guys were like equal or whatever, and all these guys were equal, I just want to collect the sort of red blue, the subsets of red and subsets of blue. They're all corresponding to the same equal number, and then just sort of count up the number of pairs between them. Yeah, and I just do this for each equivalence class for each of like so you can think of it that way. Like it's so you don't like sorting may be overkill if you actually care about the log factor, and you could do like a union find data structure type thing as well.
I guess even if you didn't have the defining vectors, you could use the greedy algorithm to find the defining vectors and then solve.
Yeah. If you didn't have them, you could like brute force for a small value of k, like depending on how like like so the way you could think about this is like k is something fixed, so I'm just going to hard code the decomposition, right? K and r are something fixed, so but I could like brute force search for it too.
Yeah, I guess in like another context where you want to solve sharp OV, but you're promised that your matrix is an equality matrix, you can solve that in linear time, I guess.
Yeah, that's what this basically should. Yeah, so sharp, whatever, satisfying pairs. Yeah, so you can think of this as like a reduction from sharp OV to like the sharp two-sum problem, where like I want to find a pair of numbers that sum to 0. I mean, this is basically equivalent to like I have red numbers and blue numbers, I want to find a red-blue pair that sum to 0, but like summing to 0, modulo a negation, this is like the same as checking they're equal, right? Like, so you can think of this as like some interesting reduction, like it doesn't make too many calls from like counting OV pairs to like counting red-blue numbers of pairs that sum to 0.
So is that how you came up with this? You're like, in this special case, we could do it, and then, what is equality matrix?
No, the way I came up with it, I started with the circuits, and it had something extremely complicated. I went through fast matrix multiplication. But then I realized that would take too long to write down, and I was lazy. But I actually came across the equality matrices because I was trying to refute the idea that like there would be these small circuits. But then the equality matrices actually made it easier for the set solver to find decompositions, because I think equality matrices are just like that much more expressive than the actual circuits. So then I was like, oh wait, I should just do everything in terms of matrices. This is more interesting. So, yeah.
I'm a bit confused about the algorithm. Like for
Yeah.
every quality matrix, I understand that you can count the number of ones that you get according to just kind of counting how many of each symbol you have in each dividing vector and
Yeah.
But you want to understand the number of ones you get in the linear combination, right? Not in a single.
Yes. So I have to, right, so like for each of these equality matrices, they have some coefficient attached to them. So I have to take the numbers that I get, multiply them by the coefficient, and just take the sum of all these counts times their coefficients. So it's like a weighted sum. Because this is an exact representation, right? So I'm exactly getting a 0, 1 representation. So this disjointness thing is like there's a linear combination of equality matrices that give me exactly the 0, 1 answer. So I'm just sort of, you can think of it as like, right, like I wanted to know the sum over all ij, such the sum of these equality matrices, like what their entries are. I'm like rearranging the order of the sum.
Oh, okay.
Rearranging the order of the sum. This is the way to think about it, right? So now I'm summing over all the equality matrices, now I'm just counting on the inside.
I mean, entry-wise, things can cancel out, but in total, the sum will be.
Yeah, they almost certainly have to cancel, right? For this to be interesting. Yes, there has to be lots of cancellations, pluses and minuses, all kinds of weird stuff happening. Yeah. So there's an exchange of order of summation trick going on. I think like half my papers have like some exchange.
I see why counting is much simpler to.
Yeah. So counting is simpler. Yeah, because detection is harder. But let me talk about how detection. So now I'm going to look at this more expressive notion where we just want a non-zero representation. Okay, so when the entry of disjointness is 1, then our linear combination is non-zero. When it's 0, we get a linear combination of 0. Okay. All right. So now we want to say we can still get an OV algorithm, but we're only detecting whether there's a pair now. But yeah, there are several things we have to be careful about here. But the proof sketch is the same, but the details are a little more complicated. So, but the same sort of Kronecker power trick still works, that we can sort of get a non-zero representation of M sub d. Remember, d is supposed to be much, much bigger and k is some fixed constant. So we can get some non-zero representation of disjointness with equality matrices. I guess, this is a different k from that case. Okay, and it can be uniformly computed. So that takes like slightly. It's more or less the same proof. But then so now we're given red vectors as before and blue vectors as before. We want to check whether the submatrix defined by these red and blue vectors contains a 1. Now it's a little more complicated, right? Because we only have this non-zero representation. So there's sort of 2 ways to get around this. If we're okay with randomized algorithms, then there's a nice little short Zippel type trick we can do. So we want to test whether the following quadratic polynomial is identically 0. So we just go over all the pairs, right? So this is just checking the disjointness, like by all the previous. This is just literally asking whether MD on AIBJ is 1 or not. Okay, so this is just like writing out the whole linear combination. So we want to know whether this polynomial is identically 0, right? Because we just have a non-zero coefficient on xi xj when the ith vector and jth vector are orthogonal or disjoint. So the idea is to plug in random values for these variables, exchange the order of summation as I described before, and now you basically do the same kind of sorting, except now you have got weights. You've got weights on the numbers in your equality matrix. So whenever two things are equal, you've got to sort of sum up the red weights and sum up the blue weights and take their product instead. But you end up making R to the D over K calls to some weighted sum problem that we can still solve by sorting. Okay. So setting these some random values, you think this just random values between 1 and 10 is enough because it's just a quadratic polynomial. So even for decent probability, you can do that. But yeah, it turns out to just be some sort of weighted sum problem. Like I collect the things which are equal. They each have some weight based on xi or yj. Like they're red, they have some xi weight. Blue, they have some yj weight. I want the sum over all their products. So like I take the sum of the weights. Like say take all of the vectors on some particular equality matrix that are taking a certain value, right? So they're all taking a certain value, and they're defining vectors like some value, say A here and here. Then they each have some weights. I just sum up the red weights, I sum up the blue weights, I take their product. And that will give me exactly the sum of the products of them that I want. So it's just exchanging the order of summation and redoing the operations. I hope that makes sense. Okay, but I can answer questions, but let me go ahead and conclude because it's like it's close to 12:30. So concluding thoughts. So in fact, like SETH implies a number of other circuit lower bounds. In other words, if we could get particular interesting circuits, we could refute orthogonal vectors. So for one, like whether the inner product mod 2, this is also something that has a nice Kronecker power of structure, its matrix. If we could get depth to neural nets of sub-exponential size for it, as also we would get a new algorithm for OV, we'd get a nearly linear time algorithm for OV. And then you could also look at other types of neural nets that don't have like the sign activation, this threshold thing, but like ReLU, where you take the sum of like, you take this linear form, and if it's negative, you output 0, otherwise you output the linear form. Even computing disjointness, like with that and sub-exponential size, would still get a better OV algorithm. Yeah, so our algorithms are effectively reducing OV to these like very simple problems by doing sorting tricks and like rearranging order summations like that. And yeah, so what other reductions are possible? Maybe we should start doubting these things. Thank you.
How do you do deterministic detection?
Oh, right, I didn't tell you. Yeah. Sorry, I started thinking I'm running out of time. Yeah, what you do, I can go back to the slide. Right, so instead of this, you make an S prime where this is squared. Okay. You square this thing. Okay. Now you're checking whether the entire sum is 0 or non-zero. So now you omit these variables, or you can plug them in as a 1, and you square this whole thing. Okay. So what are you doing now, right? Like, because this is non-zero, like the squares will just be like positive, right? So now I'm just checking whether this sum is 0 or not. So now I work over the integers, and I'm checking whether the sum is 0. Now, when I square it, right, that will blow up the number of terms. The number of terms will be r to the 2 d over k. But if I have a sub-exponential sum to begin with, that's just like squaring a sub-exponential, which is fine. But yeah, when I expand the sum, right, I'll have like r to the 2 d over k things, each of which is a product of equality matrices, which I can make an equality matrix. So that's how it works. Yeah, so you just like square the sum. But it is, like for the purposes of like fixed, algorithms like 1.35 to the dimension, it's, not as nice because you got a square there. So you get a randomized algorithms otherwise. Got it. Yeah, we need the deterministic algorithms actually to get the circuit lower bounds. The randomized algorithms aren't sufficient for that. Like from this algorithm. Yes. Thanks for asking. I had forgotten to mention. Yeah.
Okay, all right, thank you.